Good morning. So welcome you back to study lecture 1 of MA4832 on microprocessor system. So this is the first lecture for this course. And this slide shows you the motivation for you to study this course. Basically, you may be in charge of developing application within these two scenarios. The first scenario is about application with control and automation, in which controller is one of the three basic building blocks. The second scenario is the application in which there must be data exchange or data communication between two devices which connect to a network. So these are the two typical applications for you to make use of a microprocessor system. Okay, so that gives you the strong motivation to study this course. And these two videos are typical example of system or product in which microcontroller or microprocessor system play a very important role. Okay, so you see these two typical examples of a smart system or smart product in which microcontroller or microprocessor system plays a very important role. Then what are you going to study? So in the previous session, so I've mentioned about the learning objective. The learning objective is for you to become a designer of a smart system or smart product in which microprocessor system is one of the module inside. Okay, so therefore, so you must put yourself into the mindset of a user of a microprocessor system. Okay, so you must see the difference. You use microprocessor system as one of the module inside the smart product or smart system that you are going to design. So that means you are the designer of a larger system. Okay, inside the larger system, there is a module called as a microprocessor system or microcontroller. Okay, so within the system, then you are the user of a microcontroller or microprocessor system. Okay, so as a user, then you must know the problem to be solved. You must know the solution to the problem to be solved. Then you make use of a microcontroller to implement your solution or algorithm. So that is the content or knowledge and the skill for you to study in order to achieve this goal. That means you have a problem in mind, you have an algorithm or solution in mind. Then you want to know what are the knowledge and skill for you to implement algorithm or solution on the microprocessor system. Okay, so we are not expecting you to become a designer of a microprocessor system itself, okay, or microcontroller itself. Okay, so within the large system that you are going to design, you must have the capability to make use of a microcontroller to serve as a module inside the system or larger system that you are going to design. So clear, okay? So you must know your problem, you know the solution algorithm, and then you apply learn the knowledge and the skill from this course to implement algorithm and solution ARM microcontroller or microprocessor system. Okay. In order for you to use microcontroller or microprocessor system, you must have a little bit of knowledge about the inside device or inside component of a microprocessor system. Okay, so this is why we will give you an introduction about the hardware aspect of a microprocessor system, and this will enable you to better use microprocessor system. Okay, so these are the content that you are going to study. Okay, then how are going to study and what will be the exact topics that you are going to study. Then this slide basically show you the roadmap of learning, and this roadmap include two parts. On top basically is about the software part. Okay, so inside you will see we are going to learn a little bit about the architecture of the ARM microprocessor system and also the memory, okay, related to the ARM microprocessor system. But the focus will be on data representation, programming, and how to interface input data, how to interface output data, then how to undertake the data processing. Okay, so the major focus more or less is on software part. Okay, how to program a microprocessor system. Okay, then on the bottom, so you will see two modules. One is a module about the interface to input device. So typical input device could be the sensor. Okay, it could be analog sensor or digital sensor, etc. And the second module is about the interface to output device. So typical example of an output device is an actuator. It could be digital motor or analog motor, etc. Okay. Then for the scenario of data communication, then data communication usually is bidirectional. So you have an input, output all together. So this is why at the input side, we must know how to receive the data through the communication network. At the output side, also we must know how to send the data to the communication network. Okay, so basically this slide summarize what you are going to study in this course. Okay, then how to study this course in terms of hardware. The good news is you just need to configure or make use of a register, okay, to do the setup of the hardware. Then the microcontroller will do the job for you. So it's not very complicated. So as long as you know how to configure the hardware, okay, and then you must trust the microprocessor system to do the job for you properly. Okay. Then how to configure the register? Since you are the student from mechanical engineering school, then you can just visualize the register as a set of mechanic switch. For each switch, you only have two states, on or off. Okay. On means 1, off means 0. Okay. So let's say for 32-bit register, you just consider one register has 32 switches. Okay. Then you just need to know, okay, how to turn on, okay, whether you need to turn on a particular switch or not, or why do you need to turn on that switch. Okay, that is the focus of your study. Okay, which switch you have to turn on or turn off. Okay, then how to turn on, turn off the switches. So the instruction for you to use is very simple. You just choose one of these three instructions. Okay, to load a value into register, to store a value into register, to move a value into a register. You just use one of them. Okay, so in terms of instruction, it's very simple. So the major focus is on the meaning of switches inside the register. Okay, I use the term switches. It's easier for you to understand. Okay, switches for you means it's a bit. Okay, for students from a computer engineering school, we use the term bit. Okay, one bit is a binary bit. Okay, a bit means 0 or 1, and the bit corresponds to the physical hardware of a switch, because for you it's easier to understand. Okay, you know what is a switch. Okay, once you switch on is 1, switch off is 0. Okay, so it's easier to understand. So then you should not worry about the study of microprocessor system by students from a mechanical engineering school. Okay, so actually you have the knowledge and the foundation to study well this course. Okay, so you should not worry about the complexity. Okay. Then today is a lecture 1, which will show you the architecture of microprocessor system, and we will use ARM microcontroller as an example. Okay, this is like when you buy a car. Also, your role is to be a driver of the car. At least you must know a little bit the hardware aspect of your car. This is a way for you to appreciate your car, the body of your car. Then for microprocessor system is the same. So when you are going to use a particular microprocessor, then you must spend a little bit of time to appreciate, okay, the hardware aspect of the microprocessor system or microcontroller. Okay, so in this case, so we will use ARM microprocessor as an example. Then okay, it's like before you drive your vehicle, you know a little bit about the body of your vehicle. Okay, or the internal component of your vehicle. Okay, so then for microprocessor system is the same. Before you will enjoy programming, then you must know a little bit about the hardware aspect of the microprocessor system. Okay, so in the previous I mentioned there are two motivations for you to make use of microprocessor system. One is to design feedback control system. Second one is to design data communication system. Then in both scenarios, basically microprocessor system serve as a brand of an intelligent product or intelligent system. Okay, then we need to focus on this keyword brand. So we have a brand for animal, for human being. Then we also have a brand for product, for smart system, etc. Okay, so then we just look at the aspect of the brand. Then this will help you to understand or appreciate the hardware aspect of the microprocessor system. Okay, look at this example. Assume we have a two-person. Okay, they want to communicate or to have a conversational dialogue among official names. Then person A may tell person B or instruct person B to do this simple calculation. Okay, please read this question carefully and give me the answer. What is the sum of 6 plus 9? Okay, then you can start to think when person B receive this instruction or receive this data or string of data, then what happens? What is the mental activity inside the brain of person B? And here I just list down these a series of non-mental activity inside the brain. Okay, so immediately you understand. Okay, the functionality of a human brain in taking input data, undertaking data processing, then output the data. So this example it show you data input, data processing, data output. All this could be done by human brain. Okay, and why human brain can undertake such series of activity or mental activity? The reason is because our brain is a powerful machine. Okay, and you will see there are basically 3 major components on top of other, let's say, input output unit, okay, or area. Okay, the first one is cerebrum. This allow the brain to undertake a high level data processing. Okay. Second basic unit inside our brain is a cerebellum. This is like a microcontroller. Basically, it undertake feedback control system. Okay, it's like this one is very much like a microcontroller. Then besides these two, this is like a supercomputer. So you do high level kinds of thinking, reasoning, inference, etc. Okay, then this is a microcontroller. This is a supercomputer microprocessor. Okay, so then we must pay attention to the third one. You see the keyword here, we call midbrain or control unit. It's very interesting. This is very much similar to the instruction set of a supercomputer or microprocessor system. Okay, so this one is also important for you to know. Then you will appreciate the microprocessor system that you are going to study. Okay, so it's very interesting. Okay, you will see our brain also have this control unit. Okay, also have the instruction set. Okay, something like that. Okay, so then what are the characteristics of the human brain? And I just list down all these things. Okay, we are able to memorize data, or past data, present data. We are also able to interpolate new data in future. Okay, our brain can take input, can undertake computation with numbers, can play with the symbol. Okay, and also to produce output. For example, we can speak out. Okay, we can write, we can talk, etc. And we can also control our mental state. Okay, and mental capability. And we can use our brain to control the movement of our arm, our finger, our body, etc. And we are able to communicate through the language with others, or through the written language or spoken language. We are able to learn new things, especially language. Okay, we are also able to learn machine language, okay, the assembly language, etc. Okay, and also learn new knowledge, new skill, etc. So it's very powerful channel. Okay, our brain. Okay. Now look at this scenario. Okay, what happens in future? We may have a co-worker, okay, which is called as a robot. In future, that means robot may enter into our existence, and the robot may coexist with a human being. Then we may have this scenario, that means the person can instruct robot to undertake a certain action, and then you will see when the robot's brain receive this instruction, very simple one, is it lunchtime? Then you can imagine, okay, the series of mental activity occur inside the brain of a robot. So at least, okay, we can identify these this series of 5 mental activity inside the brain of the robot. And then this mental activity include input, processing, and the output. Okay, so similar to human brain. Okay, so it's quite interesting. Then we need to, okay, design something which is similar to human brain for machine or for robot. Then you may ask this question: what should be the blueprint of a machine's brain or robot's brain? And interestingly, the existing product more or less follow the existing product for microcontroller or microprocessor system or supercomputer. So more or less follow this blueprint. Then you can do a comparison, okay, between this blueprint and the blueprint of a human brain. You may find out some okay, similarity. Okay, first we have a control unit. The control unit is similar to the midbrain inside human brain. Okay, and the inside control unit, you must pay attention to this instruction set. Okay, that means depends on the instruction set. Then the capability of the microcontroller has been determined. Okay, and we also have a register. Okay, this is like a working memory. We also have a timer. because it's like a pulse, because our brain also undertake time critical application channel. Okay, so this enable also machine's brain to undertake time critical application. Then of course we also have a memory. Then machine must also have a memory to store data and store program. Okay, but in practice we may have a different type of a memory. Okay, for machine. So we have a random access memory, read-only memory, and the erasable and the programmable read-only memory, etc. Okay, and inside the memory we can store instructions, store the data. Okay, and memory has an address, has a location, and then we also have this like cerebellum or cerebrum. Okay, to undertake data processing. Then for machine, we call it as arithmetic and the logic unit. Okay, so then how to link all these things together? That means inside here we can do arithmetic operation and the logic operation. Okay, then our brain can take input from a sensory device, can also produce output to muscle or to actuator or something like that. Okay, and then for machine listen. So we have an input unit, we have an output unit. Okay, then we must connect all these together. And in general, all these connection lines are divided in two groups. One for data and one for address, and the remaining one for control signal. Okay, so this is why then we have a data bus and the address bus. Okay, then besides this, then you have an additional control signal or control line. Okay, something like that. So this gives you an overview about the blueprint of a machine's brain. And interestingly, today's microprocessor system or even supercomputer more or less follow this blueprint. Okay, so this is a way for you to appreciate, okay, the hardware aspect of the microprocessor system. Then the characteristic of machine brain more or less similar to the case of human brain. I guess you can read. Okay, first should be able to memorize the data, memorize the instruction, should be able to capture input data, should be able to undertake data processing, play with a symbol, should be able to produce output, should be able to control its own activity. Then through the interface with the actuator, then he can take action. Okay, and also can communicate. Okay, to other smart product, smart machine. Okay, in future we hope that the microprocessor system will have this capability to learn human language, to learn machine language, and also to learn new knowledge and skill. Okay, so these are the expectation in future. Today we are not there. Okay, so this is why I put the future. Okay, so this could be the research topic for us to find out the solution which will enable machine's brain to achieve these three capability in future. Okay, and then how to apply, okay, this blueprint to, okay, this blueprint to guide the design of actual brain for machine. So actually there are two guidelines, okay, for the design strategy. One is hardware architecture. So in this architecture, basically the difference is you see we separate data, memory for data from the memory for program. That's it. Okay, that means you have a two memory or one memory. The memory is divided into two parts. That means this could be a single block of memory, but it is divided into two parts. One is for the program, another is for data. We never mix up. Okay, conceptually it's joined this way. That means we have memory dedicated for program, memory dedicated for data. Okay, but physical implementation could be they are in the same space. Okay, we put together, but we cut it into two parts. Okay, one for program, one for memory. That's it. Okay. Then the old architecture, we call it the von Neumann architecture, is a mix up. That means you can store the data anywhere here. You can store your program anywhere here. Okay. But this one is no good because it's very slow. Because you see, you only have a one address bus, one data bus at the one time. You can only retrieve, okay, one set of a value, okay, either data or program, okay. To retrieve a instruction, retrieve the data, then at least you must spend two cycle of time. Or else for this one, within single cycle, you get the data, you get the program. So at least this architecture is 2 times faster, at least, okay, faster than this architecture, okay. And sometimes you may heard of this DSP, digital signal processor. DSP basically follow this design guideline, okay, principle, okay. All right. Then for the example, how to implement von Neumann architecture. So this is a typical example. So you have ALU processor the unit to process the data, and this is serve as a buffer. Cache means it's a buffer. Then you have a memory for instruction and the data. So for this architecture, this could be mixed up. Okay, they are not separate. Okay, and you only have a single set of address bus and the data bus. This is the data bus. This is the address bus. Okay. Then for Java architecture, so this is the scenario. You see, you have one set of data bus and address bus for instruction, another set of address bus and data bus for data. Okay, so that means within the same cycle, you can get the data, you can also get the instruction. Okay, all together. So this architecture is at least 2 times faster than von Neumann architecture. Clear? Okay. Then, okay, so previous slide basically just show you the result of invention of a digital computer, which are quite similar to human brain. Okay. Then next question, this is just for you to know who are the pioneer, okay, in the process of inventing digital computer. Okay, so it's good to know these people. Okay. The first one is Professor Charlie Babbage. Okay, so then you know a little bit the background. So he was from Cambridge University. Okay, another contributor to the invention of this computer is George Boole. Okay, so you may heard of this Boolean logic. Okay, so Boolean come from his name. Okay, so and John von Neumann, okay, is the inventor of the first generation of the digital computers architecture. Okay, this is why we use the name of von Neumann architecture. Okay, then we have additional person, Robert Noyce. Okay, so he is an inventor of an integrated circuit. Okay, and also invented the C programming language, and there are also people who has invented the Unix operating system, etc. Okay, so you will see a lot of people contribute to the invention of a digital computing system. Okay, then for personal computer, like you may heard two big names. One is Bill Gates, another is Jacob. Okay, so Bill Gates has created this Microsoft company, and this is a popular product, okay, in the market. Okay, all right. Then now we look at the hardware aspect of the microcontroller called as an ARM microprocessor, because for the lab and the practice session, so you are going to use the ARM microprocessor. Okay, so ARM stands for Advanced RISC Machine. Okay, basically this is a name. Okay, basically it means reduce the instruction set computer. Okay, so you remember inside the control unit we have an instruction set. Okay, so then we try to have a minimum number of instructions inside there in order to make the microprocessor system as small as possible. Okay, so then this product is an invention from this company in the UK. Okay, so this is a UK company, and this microprocessor system has been widely used in many smart product or smart system in today's market. Okay, so this slide basically show you. Okay, it's a huge range of application. So this is why then you are lucky. So you have this opportunity to study the use of ARM microprocessor. Okay, then once you learn this skill, learn the knowledge from this course, so actually you should be resourceful enough to set up your own company, to develop your own product and sell it to the market and offer job to others. Okay, so basically means that you can follow the footsteps of Bill Gates to create a company. Okay, to produce a smart product. Okay, so that should be the benefit for you to study from this course. Okay, then all the product from our company are divided into 3 series. Okay, series for microcontroller we call Cortex N, series for time critical application, that's a real-time application, time critical application. Then series for advanced application like your handphone or iPad or the high-level computing device. Okay, so A, that means advanced application. So from here you will see, so you have N series, then you have A series, okay, etc. Okay, then here you see that this is a architecture for the actual product. You may have architecture 7, ARM 7, ARM 9, ARM 11. Okay, so the R series is here. Okay, something like that. Then in terms of capability, you will see the A series is more capable than R series. R series is more capable than M series. Okay. Then in terms of performance, it's the same. A series is more performant. Okay, than R series. R series is more performant than M series. Okay. And today, this is latest news. ARM has come out the architecture version 9. Okay, this is even more powerful. Okay, but it should be okay for you to study this course with the concept or basic knowledge about the M series, because the new architecture basically to just speed up the computational power. But in terms of a concept, all these things will remain unchanged. Okay, for interface to input device, interface to output device, instruction set, and that's a way to represent data. All these fundamental knowledge will remain unchanged. So you should not worry about the change of the hardware. Okay, it's like when you buy a car, it's the same. If you are able to drive a Toyota car, you should be able also to drive a Mercedes-Benz car or BMW car. Sure. It's like when you buy a new car from, for example, you switch from Toyota to BMW, you are not going to attend a new school of driving or get a new driving license. No such things, because the driving skill knowledge are the same, remain unchanged, regardless whether you change your car or not. Okay, it's the same. So when you change the ARM processor, the knowledge and skill you have learned remain unchanged. Okay, and okay, in terms of the power, etc. This just show you what happens. Okay, etc. Then since we have a 3 series, then immediately you understand. Okay, A series for performance demanding application. R series for time critical application. For example, when you drive your car, then this is time critical. For the storage of the data into the hard disk is time critical. Okay, Then for the rest, if it's not time critical, because a lot of application may not be time critical. A lot of application may not require high performance in terms of computation. So this is why you can design a lot of smart product with M series. Okay. Then for M series, also the hardware evolve. Okay, it's like what I say. When the hardware improve, okay, there's no need for you to restudy the knowledge and skill because knowledge and skill remain unchanged. Okay, so it's similar when you change your car, you will never, okay, need to, okay, get a new driving license, etc. Okay. And here is an example of development platform for you to use, and the STM32 F7, so you can purchase from the market. Okay, when you see a name like this, basically it's a product in which you can identify. You see the ARM Cortex M7 running at the 200 megahertz. Okay, then you see the support. What is the hardware? Okay, component with this ARM Cortex M4. So you'll see the connectivity, that means for data communication. But later on, you will know this term USB and the ART eventually has a camera interface, for example, then internet support TCP/IP. Then in terms of control, we have a timer, okay, and the motor control PWM, okay, then the AC timer. Then also for the interface with analog sensor, okay. So you see, so you can attach a lot of sensor inside there, etc. Okay. And then for this course, we use this one Cortex M4 as an example for you to do the practice. Okay. Also today we have an M7, but you just change of the hardware, but in terms of knowledge skill, they will remain unchanged. Okay, so inside Cortex M4, you will see you have FPU, CPU, and many other hardware components, etc. Okay, and the good news is ARM microprocessor systems are very popular in the world. Okay, and a lot of support because there's an alliance of a partner which support the development of ARM microprocessor system. Okay, and for the learner or for student, the good news you can get the free development tool. For example, the first one, this is the one that we are going to use in the lab. Okay, so this is free. Okay, do not need to pay, and it's very, very powerful. Okay, development environment. So this is a bonus for you to study this microprocessor system. Okay. And for the hardware for you to play, we are going to use this one, TI. And you must know, okay, on top of the TI, there are many, many other companies which offer the development board for you to play with ARM microprocessor system, okay? And this is the one from a TI. So it's a TM4C123G series, okay? And this is the blueprint of hardware of this board, okay? So we have ARM Cortex M4 up to 80 megahertz. Then we have a FPU, NPU. Then we have a memory. We have a timer. We have a PWM to interface with motor. We have what else? And this is the interface with a digital sensor, okay? Interface with a motor. This is interface with analog sensor, okay? ADC, analog to digital conversion. And we also support data communication. There's an I2C bus, CAN bus, USB. This is a very low level. With this tool, you can do anything you want, okay? Invent your own protocol of data communication. So this is a serial communication. And this is the universal serial communication, receive and transmit, okay? This is for A means asynchronous. S in here is synchronous, okay? You can do both. Asynchronous for long distance communication. This is good for short distance communication, okay? So it's very, very powerful hardware, okay? And you go to TI's web page, you can watch this video, Project Zero. And this video is a free video, then you can know a little bit the introduction about this development board, okay? And in the video about okay, in the course preview, one of the video is about the vision system. You remember at that company, there's a communication between robot arm and the vision system. Okay, then you will see here is an example. So actually, ARM microprocessor allow you to interface with the vision system, and this is a typical example. Okay, so that means your ARM processor is here. Then you have a core processor. Okay, core processor can provide the interface to the to camera. Okay, so this allow you, and inside here you can do the video processing, etc. Okay, so this just show you an example, okay, of interfacing with the vision system. You can also interface this with the speech system. Okay, so then in this case, this scenario will enable your product, your system to see. Okay, and the next one will enable your product or smart product, your system to speak. Okay, so you can interface with here you see you have a Cortex M4, then with a communication interface, then you can receive the data from microphone. Okay, something like that. Then okay, the rest of the slide basically show you the this little bit of highlight okay, about the feature of the ARM. Then this just read you to read okay. And the key point here is for you to know is ARM microprocessor system is a 32-bit microprocessor system. Okay, so it's a 32-bit. Just remember, so it means one register will have 32 switches or 32-bit, etc. Okay, and this is a terminology for you to know. Okay, so by default, 8-bit means 1 byte, 16-bit means a half word, 32-bit means 1 word. Okay, then if it's use this to represent floating point or real number, then we call it is a floating point or single precision floating point. And if you use a 64-bit or 2 word to represent a real number, then we call this is a double precision of floating point. Or if you use this 64-bit to represent integer, then we call this as a double word, etc. Okay. So word means integer. Then for real number is a single precision floating point. And for integer is double word. Then for real number is a double precision real number. Okay. So this is some background knowledge for you to know. And Cortex M4 basically follow this blueprint of a design. Okay. So from here, this is a hardware control. Then ALU is here. Then you see 32-bit. Okay. Then from here, you will see we have address bus, address register. You have another address bus here. Okay. Then for data bus is here. You see 32-bit from bit 0 all the way to bit 31. And you can just imagine this is a switch 0 all the way to switch 31. Okay. For address is also 32-bit. That means a switch 0 to switch 31. So pay attention. We count the number of bit start from a 0. Okay, it's not from 1. We say we do not say bit 1 to bit 32. No, it's a bit 0 to bit 31. Okay, so this is something you need to pay attention. And you can configure the microprocessor into different mode. But since we are the user, we are not the designer of microcontroller. You do not need to pay attention to the exception mode. We just focus on these two as a user. Basically, we are here because The learning objective for this course is not for you to become designer of a microcontroller. It's to become a user of a microcontroller, which will be inside the system designed by you. Okay, let's say you design a robot. Inside the robot, you will use microcontroller. Okay, something like that. Okay, but you just need to know. Okay, this is very powerful machine. Okay, you can support other more of operation. But for us, we are here. We just focus. And this is a working memory for the microprocessor system. Working memory in terms of a register, so from 0 all the way to 15. So that means we have 16 register that serve as a working memory. Out of these 16, 3 of them have a dedicated usage. PC means a program counter. Okay, it hold the address of the instruction. Okay, then LR means it's a link register. Link register is to support the execution of a series of a function. Let's say you finish function 1, then function 1, for example, can call function 2. When you finish function 2, you must go back to function 1. Then how to go back to function 1? And the address is stored by the link register. This is the status register. Status register, for example, when you inside the function 1, you go to function 2, then you must store the status, okay, of function 1, okay. So this is this is a stack register. Stack register is for you. Stack pointer. That means when we go from one function to another function, then the context of application or computation of the function 1 must store into the memory. We need to have a copy of the memory so that we can recover it once it goes back. And this memory block has a first address. The first address is stored inside here. And such memory block to store the context of a computation of one particular function is called as a stack. Okay, stack basically means it's a block of memory to hold the computational background data. Okay, something like that. Okay, and this is a status register. It's a current program status register. Besides that, we may also have this SPSR, save the program status register. Okay, so this is the meaning. Okay, for this working memory. Okay. Then inside the ARM, basically there are some built-in file or the data. Okay, it's just for you to know. Usually, as a user, you will never modify it because if let's say we use Cortex M4, inside we have this one. We do not have this one. If let's say you use Cortex ARM series, how come the same hardware you can call it as A series, R series, M series? Basically, it's a profile will be different. Okay, so inside Cortex M4 we have this profile. R series you have this profile. A series you have this profile. That's it. Okay. Then for the bus, because this follows the Harvard structure. Okay, so then we must have two address buses and two data bus. Okay, so in this way, then we can retrieve instruction and the data within a single cycle. And this just highlight to you, we have you see we have two buses. Okay, and since we have two buses, then for each memory location, now remember we must have two address. Okay, because you cannot have the same address for two buses. Okay, so then we have two address. Okay, it's like we have a PIE, we have PIE, AYE. Okay, we must have two different names. Okay, we should not give the same name. Okay, so it's the same for since we have two bus. Then for each memory location, then we have two address. Then based on the value of the address, then we know. Okay, the signal will go through which buses. Okay. And okay, this is just for you to know the fast interrupt request. Okay, okay. Interrupt basically means is a signal. Some student may have a problem. Okay, you say, this is a big name, interrupt, etc. Interrupt basically means is internally produce a signal. It's like when you are hungry, your stomach will emit a signal to your brain so that you know you are hungry. Okay? You can ask your question, how come you know that you are hungry? Answer is what? My stomach send the signal to my brain so that my brain know I'm hungry. Okay? The signal sent by your stomach to your brain is an interrupt. Okay? Once there's an interrupt appear, then your brain can decide whether I'm going to handle interrupt or not. For example, if your brain receives the signal of hungry, you are hungry, being hungry, then you can decide whether you are going to restaurant to buy food or not. You can say, I'm not going to buy food. I am going to skip a meal. Okay, so it's up to you. And this is we call it the interrupt service. If your brain take a little bit of time to make this decision, well, I'm going to buy a food or skip a meal. Okay, this we call it as the interrupt service. Okay, something like that. Okay, but among all these internally generated signals, some of them may be urgent. Okay, you may say, for example, you have a big pain at a certain location of your body, then this could be urgent signal. Then your brain must handle, okay, the request of the urgent signal. Okay. Then for microcontroller, it's the same. We have this type of urgent signal. Then we are able to handle it. Okay. One particular example is this. Okay. That's a higher priority interrupt. For example, if you download your program, you press the emergency stop button, okay, then the whole machine must stop, something like that, okay. So you have this capability, okay, something like that. Then for the direct access memory, and for example, if you have a computer develop your program, the first practice in lab 1 is for you to practice, okay, install the software and download. And then the second practice is for you to download program into the hardware. Okay, so then you do not need to go through the CPU. For example, when you download the program, you do not need to request the help from the CPU of the ARM. You can directly download the program from your computer from here to the memory. So through this direct memory access capability. Okay, it's this scenario. Okay. And this is to provide, okay, interface between the microcontroller and your development computer. Okay, so that you can develop your program with integrated development environment and debug it, etc. Once everything is okay, then you download through this link, okay, into the development board, okay, something like that. Okay, then in terms of development environment, so this gives you a very nice user interface for you to implement your solution, okay, with the instruction set, so that the developed program could be performed by the microprocessor system. So now from this slide, now you understand you must put yourself as a user of a microprocessor system. You know your problem, you know the solution, you know the algorithm. Then your job is to implement algorithm or solution with instruction set to come out a series of instructions. Then this series of instructions could be downloaded into the microprocessor system, then let the microprocessor system to perform, okay, all these instruction set, okay. And then how do we translate or implement your solution or algorithm into a series of instructions? And the good news is what you have a software development environment called as IDE, integrated development environment, okay. And the next question is, what will be the procedure? How are you going to translate or transform your algorithm into a series of instruction. So basically, you must follow. As a student, you must follow all these steps of a guideline. But one day, if you become very professional, eventually you can skip this step. For professional developer, you can directly write the instruction set from algorithm or equation. But as a beginner, I do not believe you are a professional developer. So you must follow all these steps. First, translate your algorithm into flowchart. Okay, for example, let's say electric toaster. Okay, so you have a main start, then you get the input. Okay, then you start, then you cook. Okay, then you get the input to see the cooking condition. Okay, well, okay, when the start has been pressed, you cook. Okay, if you once you reach certain state, then eventually you can exit. Okay, so this just for this one is to turn on the cooker. Okay, so that means you have a program constantly monitor the start button. Okay, when the start button is pressed, then you will turn on it. Once you turn on it, this will execute this one. Okay, that means inside here, basically is all these things. Okay, if it's not pressed, then just stand by, wait, keep checking. Okay, whether it has been pressed or not. If it's yes, then enter here. Enter here means you do this. Okay, so you turn on the heater, then you input the temperature, okay? Then to see whether it exceeds the desired value or not. If it's yes, then you turn off, then you return. If not, you continue to do the cooking, okay? Because the temperature is still cold, okay? And once reach a desired temperature, then you start to stop, okay? So you must translate to exactly describe the procedure of your algorithm in the form of a flowchart. Okay. Then next step is from the flowchart. Then you do the translate into the function. Okay, the program function. Okay, so you have a main function is here like this, and inside the main function you have another function. Okay, here. Okay, something like that. So and the flowchart to program in terms of a function. And after that, for each function, then you must implement the instruction. So inside the function, you have a subset of instruction, something. Okay. So then to do all these things, the good news is you have this integrated development environment. Okay. So this will show you this is your program instruction set. Then the memory, the storage of your program. So this is a program that is readable by human, and then this is stored inside the memory for program. Okay, then this is the working memory of the ALU. Okay, so you will have a 5 practice for you to gain knowledge and skill with this one. Okay, so you should not worry about the this slide. You say you cannot understand all these things because you have a 5 practice. So by go through all these 5 practice, and then immediately you understand all these things. Okay, so it's quite powerful user interface. Okay, and typical applications, a way for you to implement or in terms of the block diagram. So these are the 3 typical type of block diagram in the sequence, in series, condition, and loop control. Okay, and when you mix up all this, then you can create very complicated application. Okay, so these are the 3 basic the structure of instruction. Okay, structure, the series or sequential structure, conditional structure, and the loop structure inside your block diagram. Okay, and for example, you can put all together. You see, you have 3 in parallel, and then for this one conditional, you see you have a 2, and the loop you have a 1, etc. Okay, so. And okay, this highlight to you the hand-on practice. For lab 1, basically is for you to build up the basic skill for you to use IDE. Then for lab 2, 3, 4 is for you to play with the hardware interface, with the sensor, with the actuator, etc. Okay, and okay, pay attention. Due to this, the things may change. Okay, for lab 1, I'm in charge of lab 1, and Dr. John Han, we are in charge of lab 2, 3, 4. Okay, so this is why I just preview lab 1. For lab 1, we have 5 practice. Okay, so you are going to spend 5 weeks to study or to practice lab 1. Okay, and practice 1 is in week 1. But it happens week 1 we have National Day, so it's a public holiday. But good news is this one you do not need to come to the lab, so you can just follow the lab manual, do it at home. Okay. Then 2, 3, 4, 5, you have to come to the lab because you need to have access to the lab equipment. So for each week, we have a 2 hour for you to stay in the lab. So we are divide you into 2 groups. You have a group MA1, group MA2, okay? And each group will have access to the hardware for 1 hour, okay? So this is a planning. So you follow the planning, okay? So instruction, all the detail will be in the lab manual for lab 1. So I'm not going to repeat it, okay? And you follow all this instruction, okay? And for practice 1, you follow, okay? Okay, this is just a copy of from the lab manual, okay? So you must study detail, and we also provide you the media video, okay? In case you get lost, then you read this one, okay? So watch we also give you the example program, okay? You should not worry, we have a example program there already. As long as you know how to read, okay, understand the meaning of the example program, good enough, okay? And we also have additional media video for you to watch, okay? Etc. Okay. Then we move on. Then for practice 2, this is why 2 you must go to the lab. This is just for you to see. Use this, you develop your program, then you download your program into the hardware, etc. But good news is we have another video show you how to do it, okay? So you should not worry, so you are basically guided, okay, by all the learning material, okay? And for practice 3, then you need to go to the lab, for example, play with the switch, etc., to read in the data, and more detail in the lab manual, okay? Then practice 4, again, you need to go to the lab, okay? Because without the hardware, you cannot do it. More detail is the lab manual, okay? Then lab 5 is the same, okay? So you must have access to the hardware, and that is why you need to go to the lab, okay, etc. All right, so that's all for lecture 1, which is about the hardware architecture of the microprocessor. This is for you to appreciate, okay, to like the hardware that you are going to play. Okay, this is similar like the case when you purchase a new vehicle, then at least you must spend a little bit time to appreciate the hardware of your new vehicle, okay? If this is the first time for you to use Cortex M4, so it is good for you to spend a little bit of time to appreciate the hardware aspect of Cortex M4, okay? But in addition, so remember, we will give you lab 1 for you to gain the knowledge and skill with the use of integrated development environment, okay? So you are going to spend 5 weeks to master the knowledge and skill related to the IDE, okay? So you should not be worried about the, okay, the difficulty or any difficulty related to the study of this course or not, okay? So I hope you will appreciate the benefit offered by this course and enjoy the study of the course, and set some expectation for you, because once you study well of this course, eventually you could be resourceful, and you could be ready to invent your own product, okay? with this microprocessor system inside, and then eventually you can venture into the startup, etc. All right, so that is an extra benefit for you to study this course. Okay, all right. Thank you for your attention, and see you in lecture 2.